Super excited. My name is Sally Phelps, and I am the Director of External Programs and Partnerships here at Olin with a focus on alumni engagement. And yes, welcome to Frank Talks. This is our monthly series of alumni doing good in the world. Very excited to say that last month we graduated our 17th class from Olin. So now we have a whopping 1,304 alumni out there, and they are doing amazing things. Brendan Quinlivan, our guest tonight, class of 14, is certainly no exception. After graduating from Olin, Brendan completed his PhD at the Harvard School of Engineering and Applied Sciences. An NSF graduate research scholar, Brendan's research focused on wearable robotics, lying at the intersection of robotics, functional apparel, and human movement science. At Harvard, Brendan and his colleagues developed soft exosuits. I've been practicing that because I kept saying it wrong. Exosuits. Brendan, hopefully you're better at that than I am.
Hopefully.
Brendan and his colleagues developed soft exosuits that can reduce the energy expenditure of walking and running. Additionally, Brendan developed a lightweight, low-profile robot for at-home gait rehabilitation of stroke survivors that was licensed to Rewalk Robotics and recently received FDA breakthrough device designation. Yay, congratulations. After completing his PhD in 2020, Brendan joined VERVE Motion, a startup in Cambridge, building a wearable robot to reduce fatigue and back injury for industrial warehouse workers. So as you can see, from soldiers to stroke survivors to warehouse workers, Brendan has a passion for improving people's quality of life through technology that they can wear. Please join me in welcoming our guest tonight, Brendan Quinlivan. Welcome, Brendan.
Thanks, Sally. So maybe I'll just jump right into it then. Thanks, Sally, for the introduction. You basically did my whole talk, and so now no one needs to know what I've done. But as Sally mentioned, I've been working for the last 10 years on different wearable robotics. And so I guess before we launch into it, the question is what is a wearable robot? I'm actually gonna optimize for screen sharing. Perfect. Okay. So what is a wearable robot? So if you're not familiar with what an exoskeleton or wearable robot is, you might think of something like Ironman, a high-tech suit that dons itself, is super lightweight, it allows you to move around very naturally, and even gives someone like Robert Downey Jr. superhuman strength, where he can kick a car out of the way, just like this. But in reality, when I started this journey back in 2012, what an exoskeleton really was something more like this, where it was a rigid weight-bearing exoskeleton, like something shown in the video. There's rigid linkages that span the lower extremities and go from your hips all the way down to the ground. And as you can see, when someone's wearing something like this spinal cord injury patient, they are walking with a little bit more of a robotic, unnatural gait. And so this is really where the technology started, like I said, back in 2012. And in this case, this was for spinal cord injury patients. And it's very important to enable somebody who wants to walk, who didn't have that capability to do so. But you can also look at this for healthy individuals trying to reduce the burden of carrying something like this heavy backpack. So this is a device out of MIT where there was a heavy amount of load in the backpack and they're trying to distribute it down to the ground. In this demonstration from my former professor, Connor Walsh, they showed that you can reduce 85% of that load directly into the ground, but it ultimately made it harder to walk. It made it 11% more energetically costly to walk. And that was really due to three different reasons. One, there was significant inertia added to the lower extremity joints by all of those rigid linkages, because you have all that heavy metal that now you need to move with you in addition to your normal lower limb. And then additionally, with these rigid exoskeletons, you need to align the biological joint with the exoskeleton joint. And so with any misalignment between those two can make it more difficult to walk. And then finally, you or I have hip and ankle joints that move in 2 or 3 degrees of freedom, whereas something like this robot limits that down to 1 single degree of freedom, where you're only moving in the side plane or the sagittal plane. And so it adds kinematic constraints by adding this rigid exoskeleton. So what I've really spent the last decade working on, from 2012 up till now, is how do we make these exoskeletons useful, but how do we make them soft? And how do we address all of those problems that I just kind of outlined? So I started this journey back in 2012 when I was between my sophomore and junior year at Olin, where I did a summer internship at the Harvard Biodesign Lab. So this is actually an important shout out to another Olin alum, Leif Gentoff, who is now a co-founder of Right Hand Robotics. He actually made the initial introduction for me to my professor at the Harvard Biodesign Lab. I interviewed with Leif for a different position and ultimately didn't get it, but he recommended me to this brand new professor who was starting. And he said, I think your interests really align with the Harvard Biodesign Lab. And so I started there as their first summer intern back in 2012. And so you can see this picture is an attempt at an engineer trying to sew functional apparel. And as you'll see over time in my presentation, it got a lot better when we had real functional apparel designers do it. But this was the first prototype example when I started my first internship, where we were just trying to hack things together and figure out, what is a soft exosuit? What does that mean? How do you apply assistance to the body in a way that is soft, compliant, and doesn't add a bunch of weight to you? And so the way we did that was really kind of addressing the 3 kind of major areas that I mentioned before. We wanted to minimize the weight on your lower limbs. We wanted to provide assistance that was intrinsically aligned to the biological joints, so you didn't have any misalignment between a rigid hinge joint and your body. And then we also wanted to minimize the amount of kinematic constraints. So can we just let you move totally freely like you normally would and not place any rigid linkages in your way? And so we did that really by having 4 different parts of the system. We had a structured functional textile, meaning there was like apparel components that you attached to your limb and kind of wrapped around and Velcro closed. And those provide anchor points to attach and apply assistance. We also had IMUs, or inertial measurement units, which are sensors that allow you to detect how the person's moving. So we can detect how you want to move and then apply assistance at the right time. So unlike maybe a rigid exoskeleton for a spinal cord injury patient where we're telling you how to move, here we can detect your intent and then provide assistance at the right time. And then on the right side of the picture, you see we had all of our heavy components, all of the motors, the electronics, the batteries, everything centered right at your trunk, kind of in the backpack. Because as you can imagine, it's a lot easier to carry 10 pounds in your backpack than it is to carry 10 pounds on your foot. And so we concentrated all of the actuator components, all the electronics there. And then we use what's called Bowden cables, which are basically bike brake cables, to transmit that force that we're generating at the actuator at the waist all the way down to some point on your limbs to provide the assistance there. And so how that assistance actually works is we have something like shown here, looking at the ankle, for example, when we want to apply plantar flexion or assistance, which is when you push off the ground with your toes. Here we have kind of a calf wrap, a functional apparel wrap in green, and then we have the cable coming down, the outer sheath of the cable shown in black, and then the inner sheath kind of shown in gray. And so when you have that, if you can see here, yeah, outer sheath in black, in the inner sheath in gray. And so when you pull on that inner cable, you generate a force within that. That force is a certain distance away from the center of rotation of your ankle, and therefore we're applying a torque about your ankle. We're giving that assistance. And so that torque of your ankle is basically in parallel to your biological muscles. And so here's a video of it in action, looking at the ankle. You can see on the right, kind of right as your heel's coming off the ground, the cable pulls and gives you a little bit of a boost. And the idea behind that is by providing that assistance in parallel to what your underlying muscles are doing, we can reduce the torques and powers that your biological muscles are trying to produce, and ultimately make it easier or less energetically costly to walk. And so, as you can imagine, as Sally kind of indicated at the start, it's a very interdisciplinary project. And so here you have, this was the Harvard Biodesign lab I was working in. It didn't look like this when I started, but it did when I ended. We had functional apparel designers creating the wearable components. We had biomechanics experts working on estimating the biomechanical impact of these devices, and in that case, measuring the energy expenditure of when someone's walking. And that all ultimately results in something like this wearable robot as somebody walks off. And so there's a huge robotics component, there's a huge biomechanics component, and there's a functional apparel component. So it's very interdisciplinary, which is really interesting coming from a research perspective, where you get to have your hands in many of these different areas, and there's so many different minds coming together to try to create the best device. So I want to start by maybe talking a little bit about the functional apparel component, because that's the maybe part most foreign to many owners. The robotics part we get. We know how to build good actuators and figure out when to provide the assistance, but the apparel component is maybe a little bit more foreign. And so over the 10 years, we evolved from, like I said, something on the far left, which is what we called fancy pants, when me and one other engineer were trying to sew some McKibben actuators, which are kind of pneumatic actuators, into a pair of pants and just say, can we tug on somebody at all? And then over that, like 8 years that I was in the lab, 2 as a summer intern and 6 as a PhD student, we evolved over time and really brought on functional apparel designers who could do that sewing and apparel design for us. And they were much better at it, obviously. And so in that like soft interface design, there were kind of 5 key components that we identified, and 5 key principles for how you interface with the human body. One is to provide anchor points of the human skeleton. So if you're trying to anchor a lot of force, try to use a bony landmark like the waist, your pelvis almost. In addition, try to leverage like different parts of the human geometry. So if you're trying to provide assistance to your calf, try to put all of that force, that reaction force above the calf, and then that will help anchor as you try to pull down on it. And then use high friction and high compression materials to try to really stick to the human body. Because as you can imagine, we're very squishy, and it's not very efficient to pull on something that's squishy. And so we need to find a way to do that effectively. And then finally, use materials that are stiff in the direction that you want to pull, but then still conformal to the body, so you can make a nice wrap around the body. But then when you pull, you don't lose a lot of energy stretching the material that you're pulling. And so that's like soft exosuits in a nutshell, but I'm going to focus on kind of 3 main applications that I've looked at over my time. First, we started with improving walking efficiency, or making it easier for healthy individuals to walk. And then we focused on post-stroke gait rehabilitation, both in the clinic and at home for stroke survivors. And now finally, as Sally indicated, I'm working at a company called VERVE Motion in Cambridge, and we're trying to reduce back pain and back injury of warehouse workers. So to start with the healthy individuals, really, you can kind of look at this as the input-output optimization problem, where you're inputting some type of exosuit power or augmentation power, which is just that force in the cable times the moment arm and your angular velocity, the power you're inputting into the system. And then you're looking at getting some metabolic reduction or energy cost reduction. And we estimate that energy cost reduction by measuring the oxygen and carbon dioxide you're breathing in and out. And so in the video you may have seen before, someone was wearing this kind of blue mask, and that was measuring the oxygen and carbon dioxide mixture in their air. And from there, we can estimate how much energy someone's consuming. And so when I started this, no one had ever shown a metabolic reduction for wearing a wearable robot before. But Philippe Malcolm, who is now a colleague of mine, formerly was at the University of Ghent in Belgium, was the first person to ever show a metabolic reduction relative to normal walking. And he showed a 6% reduction in energy expenditure with a robot that he had designed. And so that was right in 2013 when I started my second summer internship between my junior and my senior year in college. So wearable robotics is very much in its infancy, or soft robotics, I should say, is very much in its infancy. And so when I started my PhD, very much focused on trying to look at that relationship between the power we put in and the power we get out. And so ultimately, I ran a study with a colleague of mine, Sanju Lee, and we looked at 4 different levels of force. And ultimately, we were able to show that we could reduce the energy cost of walking by almost 23%, which at the time of the publication was the highest that anyone had ever shown. And so we got a nice paper in Science Robotics out of this. But as the Reddit nerd in me was more excited about the fact that when we published the paper, we were trending number 3 on Reddit that day, where people were very excited about this 23% metabolic reduction. So that was kind of cool. This acknowledging in academia is cool, but when it gets onto Reddit, it's a little more exciting. And so we proved this in the lab. We could reduce this energy consumption, and ultimately we designed, with many colleagues in the lab, they designed a device that was portable. And so here's an example. You kind of saw it in a video earlier of what that final device looked like, and we could reduce walking efficiency with this device. So again, the actuator's kind of in the middle, and there's all of these cables spanning. And so we were, in this case, assisting both the hip and the ankle. And ultimately, we were able to show that we could reduce the energy cost of walking with a mobile system relative to normal walking by about 15%. So that was very exciting to go from, when we started this, no one had ever shown something, to 23% in the lab to 15% outside the lab for walking. But if you can do that for walking, I guess the next question is, can you do it for running, or can you do it for both? And so this wasn't my work, but this was work from one of my colleagues, Jinsu Kim, and he showed that we could create a device which assisted the hip that could reduce the energy cost of walking for both walking and running by about 9% for walking and about 4% for running, relative to normal walking without any device on. Because as you can imagine, when you put the actuator on, it gives you a little bit of cost to carry that extra weight. But we could show here and in the last study that you could overcome that extra weight and still have a benefit to your normal relative walking. And so we did this. We showed walking, running, we showed both together. So like, what was the next step? And really the next step was to focus on post-stroke gait rehabilitation. And so why stroke? We focused on that because it was the leading cause of serious long-term disability in the US, with over 7 million stroke survivors living in the United States and over 800,000 new strokes every year, with a direct cost of about $45 billion to the US every year. And so when a stroke survivor has a stroke, many of them develop what's called hemiparesis after the stroke, which is partial paralysis of both the arm and the leg, usually on one side of the body. This often results in very asymmetric, slow, and inefficient gait, kind of as you can see in the video in the top. So a person has normal function on their non-paretic side, their not affected side, but then on their affected side of the stroke, they're limited in both their ankle capacity as well as their arm capacity. And so ultimately, this energetically costly gait, the asymmetric, slow, and inefficient gait, results in difficulty in community reintegration and limits many of these individuals to sedentary lifestyles, and ultimately can reduce the overall quality of life. So the primary reason of this deficit is impaired ankle function, as I talked about. Why are individuals walking slower? If you look at a gait cycle, which is a one walking cycle, where you see heel strike of one leg all the way to the heel strike of another leg, the main deficits that we see are at the ankle: reduced propulsion or push off when you're trying to leave the ground. So how hard are you pushing into the ground? And then increased drop foot in swing, which is when you're trying to pick up your foot to clear the ground. Many stroke survivors have difficulty pulling up their toes and can often catch their toes and result in trips or falls. And that's what's called drop foot. And so because of this drop foot, many stroke survivors end up using what are called AFOs, or ankle foot orthoses, to try to stabilize that ankle and keep it locked at 90 degrees to prevent them from catching their toe. This then further reduces the propulsion you can make because your ankle's kind of locked at that 90 degrees, and further reduces the speed at which an individual can walk. Also, these deficits kind of travel up the limb to the hip, And we see that people who have reduced propulsion or reduced or increased drop foot, they tend to hike their hip or circumduct their hip, meaning they pull their hip up to help their foot clear the ground, or they swing their foot to the side to try to, again, help their foot clear the ground. And so often these gait compensations and this reduced plantar flexion or the reduced push off ended up making that gait more and more inefficient. And so to combat that, many stroke survivors use physical therapy or physical therapy rehabilitation to try to increase their gait speed and kind of address some of those compensation mechanisms. And so most physical therapy kind of targets increased intensity, high dosage, and high specificity of that training. And they do this in an environment that is both in the clinic and then at home. So if any of you have gone to physical therapy, usually you'll go in for 1 or 2 days a week, and then they'll prescribe you an at-home exercise program to say, okay, the 5 or 6 other days that you're not in the clinic this week, try to do these exercises at home. So when we started this, we first targeted the in-clinic physical therapy. And so how can we enhance that physical therapy? How can we make it more intense? And how can we make it more specific to the individual? And so my colleague Jaehoon Bae and Lua Wad developed a device very similar to the one that we had developed for healthy individuals to reduce energy. We targeted this for stroke survivors, and they targeted, again, that affected ankle. So just one side of the body, how do we increase that propulsion in the toe clearance? And so a video of how that works is shown here. So as the person's coming and as their foot's about to leave the ground, we pull that back cable up to provide a torque assistance to it. And then as their toe is about to leave the ground, we push the cables out in the back and we pull the one forward in the front in order to help their toe clear the ground. And so the pull forward in the front, and then we hit the ground again and we release that front cable. And then it just is a cycle. And this helps people reduce some of those compensations and try to have a more natural, more energy efficient gait cycle by training with a physical therapist in this manner. And so they did this. They showed in a number of biomechanics tests that we ran in the lab, where we had amazing volunteer stroke survivors come in and test our device for us. They showed that you could increase that toe clearance and propulsion. They could reduce those gait compensations that I mentioned, and overall increase the symmetry and improve the walking economy. And this technology was ultimately licensed to Re-Rock Robotics, which is based in Marlborough, Massachusetts. And they're a company that has a rigid exoskeleton for spinal cord injury. And they're now selling this to physical therapy clinics. But when I kind of came into this problem, I finished the healthy work, and we got to a point where we're like, okay, healthy work. My colleague Jaehoon had worked on this device and made it for in clinics, but how could we get it so that it was at home? And really, there's a lot of barriers at the moment. The device that we had designed was not meant for that. It was quite bulky, it was very expensive, and needed a physical therapist to help don and operate it. And so at the time when I started this, probably 4 years ago, there was no robotic device that currently existed for at-home gait rehabilitation. And so my vision for this project was to develop an at-home gait, at-home ankle device to assist post-stroke patients, which supplements that in-clinic rehab and allows for high-intensity, context-specific gait training at home, meaning they can get that workout, they can walk faster and further, and they can do it in their own community. So the vision was really, on a Monday, you come in, you train with a physical therapist, and then they kind of help you set up your settings. And then maybe you're at home for the other 6 days of the week, like on Wednesday and Friday, and you're operating it by yourself on your phone or your tablet to control the device. And it's easy enough for you to use. The physical therapist could come and check in on your data and see how you're doing. But this was kind of the vision that we had developed. And so ultimately, I worked with some of my colleagues to design a device that fit these needs. And we ultimately designed a device that was about 4.3 pounds in total. And so it had a little actuator, a small rope winch actuator that you kind of mounted on your calf. It had an electronics and batteries that, again, you wrapped around your waist to anchor most of the weight up there. And then it had a little passive toe-up brace that we specifically designed to allow you to have that assistance to keep your toe up, but then we could pull on the back to give you that propulsion assistance. So we weren't locking out your ankle, but we were just providing this passive brace to kind of enable that safe operation. So you could just take the actuator off and you could walk around normally and still get that toe up assistance, or you could, and then you could pull against it when you added the actuator to get that increased propulsion and help you walk faster. And so this was the result of that. And so we developed an app, a phone app for them to use the device and operate it. And this was one of our volunteers who helped test our device. And so, as you can see, he's donning the device. This volunteer in particular had good function on both of his hands, so he used it. But we also had volunteers who had only function on one of their hands and were able to don it with just a single hand as well. And so here he's putting on the brace, he's slipping on a shoe, he's using a shoehorn, which I will admit is a underutilized piece of technology and came in very beneficial for a lot of our testing. And so, and after he laces up his shoe, you'll see he'll just grab the actuator. And we had, again, a lot of functional apparel designers help with this as a little magnetic closure for the belt to make it easy to don, and then they would slip the actuator on. At the time when I was running this in 2020, we hadn't made the sensors Bluetooth, so we hopped in and threw the sensors on there, but now they can be Bluetooth. So now the user like opens up their phone app, turns the device on, so now it's ready to use, and then he's good to go for his training. In this case, our user also loved to track their steps on their Apple Watch, so you'll see he'll turn his Apple Watch exercise on, and then we would go about our training. So the training that we actually ran was right in the middle of the pandemic. So I was in spring of 2020, had designed the device, we're all ready to go, and then the pandemic hit. And I would advise that that's not the time that you want to try to be running human subjects tests on populations such as stroke survivors. And so after a lot of work and a lot of time, we ultimately found a safe way to do this. And so we ran an at-home exercise program with one chronic stroke survivor who we went to downtown Boston and tested. That's Commonwealth Ave, for those of you familiar with it. And so we went there for 4 weeks, 3 days a week, and trained with this individual. And so what we did, shown here, is that we had this one stroke survivor when we ran a gait rehabilitation program over 4 weeks, where we had evaluated his speed and efficiency before the training. We had 10 training days across 4 different weeks, where some of them were guided by the physical therapist as if it was in a clinic. And then 2 of them were run at, without the physical therapist guiding them as if it was an at-home visit, as a way to simulate that type of approach. And then after that 10 days of training, we evaluated some of the same biomechanics metrics we looked at afterwards. And so I won't bore you with all of the details of the biomechanics, but essentially we ran what's called a 6-minute walk test, where the individual walks as far and as fast as they can for 6 minutes. And we saw that on the first day, before they even started training with the suit, they could walk 30 meters further with the exosuit assistance. And that was very exciting, because what's deemed as the minimally clinically important difference is 34 meters. So that's when a clinician would say, actually, that's a meaningful improvement. And so on the first day, just turning the suit on, they could walk further and walk faster. So train with that higher intensity. And so then after that 10 days of evaluation, we looked at his normal condition, like walking without the suit, before and after, and he was able to walk 72 meters further. So almost double that minimally clinically important difference, which is very exciting to see that after 10 days of training with something like this exosuit that helps you walk faster and further, it can have these meaningful impacts on your gait outside of using the suit. So after you put it aside, you're still able to walk further and faster. And so that was very exciting. And that was kind of the culmination of my PhD, was in downtown Boston on Com Ave running this test, getting a lot of people to stare at us like, why is there someone walking around in a robot? Ultimately, as Sally mentioned, this technology was also licensed to Rewalk to add to their rigid robot and their in-clinic robot. But more excitingly, they received FDA breakthrough designation, which is very difficult to get, and was very exciting to see that this technology was deemed important enough to get that designation. So that was kind of the culmination of my PhD, about 6 years worth of work on wearable robotics. And then in 2020, right after I graduated, I joined Verve Motion, where we are working on a device to prevent back pain. So taking that 8 years worth of work at Harvard and trying to apply it to prevent back pain and back injury. And why are we focusing on that? It's because there's many people, particularly those working in warehouses, that see injuries, including 1 million back injuries every year in the workplace, with over 260 million days lost due to those injuries, and over $14 billion in direct costs to US employers. And so it's something where we can keep people safe, but also hopefully save some of the employers money at the same time. And so right now, like I said, we're about 1.5 years old. We spun out in 2020, and most of us spun out of that Harvard Biodesign Lab using the previous 8 years worth of work. And we're really targeting those industrial workers who lift as many as 2,500 boxes a day. They're working 8, 10, 12 hours a day, lifting anywhere from 20 to 30,000 pounds a day. And so that's just a lot of strain on your back. And so we're really working on having this device reduce that back pain and back injury. And so we're in a number of warehouses right now, across mostly in grocery distribution chains. And so who knows, maybe your groceries are being picked by an exosuit and you don't even know it. That is pretty much all I had to say today. And so I just want to acknowledge everyone else who worked on this, my advisor, Connor Walsh, and a bunch of my other committee members, Lou Awad, Terry Ellis at Boston University, and Robert Wood, who's at Harvard in the robotics. And then all of our study participants who suffer through all of the biomechanic tests for science, and then everyone at the Biodesign Lab and at my current company, Verve Motion. An important shout out though, as I mentioned Leif earlier, who is an Olin alum from 2009, gave me that initial introduction. And so over my last 10 years, many other Oliners have joined the cause for wearable robotics. So just wanted to give a shout out to them. Asa Eckert-Ernheim was a staff member in the Biodesign Lab for 5 years. So a lot of the actuators I showed were designed by him. Miles Cooper and Harrison Young are PhD students in the lab that have joined since I started. And then Brooks Willis and Gabe Greeley are 2 Olin alum who both were staff members in the lab for about 1 year. And then at my current company, of course, we needed to bring more owners along. So Cecilia Deal is working with me as a project manager at Verve. And then June Kong, who's a current Olin student, did a XLP in the fall, another program that Olin has for current students to work at companies while they're still on campus. And so it's exciting to see that so many other Oliners have joined the wearable robotics community along the way. And so with that, I will stop and I'm happy to answer any questions you have about wearable robotics or my time at Olin or anything like that.
Thank you, Brendan. Feel free to just raise your hand or to put your question in the chat if you like. I'm glad too that you put up that slide with all the different.
When I was going through it, I was like, "There's been a lot of other people over the years that have joined the cause." So it's exciting to see, everyone.
You see the question from Nicole, Brendan.
Yes. How expensive is it to replace parts? Which parts break down the fastest? So in the stuff that I was working on at Harvard, it's usually the cables that are pulling on people that break more often. So Bowden cables, just like your bike brake cables, are things that you might have to replace every now and again. And the same on our current device in in the VERVE motion, the company I'm working on, there's like a little ribbon that provides the assistance. And so that is something that you have to maybe swap out every year and a half or so. But it's usually we can get away with not replacing many of the components. Okay. Hey, Allison. Thanks for your question.
Allison. Wonderful
Yeah.
to see you.
So Allison asked, what advice would you give to a first-year student who wants to study robotics in grad school? What classes or practical experience are important? So I'm probably a bad example of this because I didn't actually study robotics at Olin. I actually graduated with engineering with a concentration in biomechanics. So I ended up creating my own major and being more on the biomechanics side, and then getting more into the robotics during my PhD, which was an interesting transition. But there's a ton of opportunities and many different faculty members, particularly at Olin, that are studying robotics. And so getting in there and just having experience doing research and working with a faculty member, I think is really important. At Olin, I actually did engineering education research with Zhenya, which has totally nothing to do with robotics, but it was a great experience to like learn how to do research and how to ask these questions and how to write a paper and how to organize things in a very methodical way. And so that was a great experience, again, totally outside of robotics, but just getting that connection with a faculty member and being able to understand how to do research was super valuable. Nicole, thank you for your question. How hard was it to realize or identify when you needed to step back from the project and ask for help from others in the same field as an expert in different fields? That was like super, super important. So early days, like I said, it was like me and one postdoc, like someone who had graduated with their PhD, that were working on this project. And we were just like trying to sew some pants together and trying to like attach things to the human body, and then trying to figure out, how do you measure this? What is biomechanics? And so early days, we tried to do everything ourselves, and then very quickly realized that that was not feasible and that other people had areas of expertise that were valuable. So we ultimately brought on functional apparel contractors and then full-time functional apparel designers to help us do some of that components, because we realized there's a whole industry out there that you don't really see as an engineer, of sourcing the right materials and finding materials that are compatible with humans and that have certain properties. And how do you build that into a design package? And so one of the things that's really interesting is, as a mechanical engineer background, you create these like drawing packages that are super detailed, that have all of the like details of where every single screw hole is going to go and the specific measurements. And so apparel designers do the exact same thing. It's called the tech pack, and it's like very, very detailed, and exactly where are you cutting and sewing every single piece of material. And if you'd see one of those, it's like, you'd be shocked at how much design goes into it and how technical that work really is. And so we didn't know what we didn't know when we started. And I think bringing on apparel designers was a key part of what really allowed us to be super successful. One of the things that I didn't mention was that wearable robotics, the Warrior Web program, where we were trying to reduce the energy. We were a brand new lab, and we went up against 20 other labs in this, what was called the DARPA Warrior Web program, where everyone was trying to reduce the energy as much as possible. And so they started with 20, and and they whittled it down to 10, and then they whittled it down to 5. And somehow there were 2 of us left at the end. It was our lab and Boston Dynamics. And at that time, Boston Dynamics got bought out by Google, and Google said they were no longer doing government contracts. So we were the only ones left at that time. And I think a big part of that was realizing what we didn't know, and bringing on physical therapists to help give that biomechanics insight, and bringing on apparel designers to help design these functional apparel components that engineers are not the best people to design it for. Yeah, but thanks for your question, Nicole. Arjun, I'm a high schooler who is interested in pursuing engineering and robotics. what kind of practical knowledge would you recommend me to build on? So with robotics, there's many different areas that you can get into, right? You can get into the software side and learning C and C++ to understand how to do the firmware, and which is the software on these robots, and that runs the mechanical and electrical components and tells them how to talk to each other. You can get into the mechanical design side where you're designing the actual actuators, or you can get into the electrical design side where you're designing the electronics components. And there's so many ways in robotics to try to get in. I somehow ended up in robotics and didn't even do first in high school. I was one of the anomalies there. But yeah, I would say just getting involved, finding someone who has experience, like a faculty member at Olin who can take you under the ring and show you what robotics, and figuring out what you're interested in, software, mechanical, or electrical, and just pick one and try it out. That's what I would say. Scott, are Bowden cables just steel, or are they slightly more elastic to reduce shock load? How much have battery tech changed over the last decade? What can you do? Have you got any guesses of the next big step forward in your industry that you can share? Yeah, so I would say Bowden cables are a steel cable, but they're like a braided steel cable. So there is some give in that cable. So it's usually like probably 5 or 6 strands wounded together. So they are somewhat elastic, but mostly what we were looking at is having like the stiffest cable possible, because you want to provide that assistance and not lose any energy. You want to pull on that person and not like lose a lot of energy stretching the cable. So the lack of elasticity was something that we actually enjoyed. Battery technology has definitely changed a lot, and is probably one of the biggest things that's limiting us, and was limiting us and still is over time. Is to power these systems, you have to have batteries, and that's probably the heaviest thing on here to walk. So we had some soldiers with one of the hip devices walk 10, 12 miles in the device and we had to, early on, we would have to swap out batteries because they couldn't last for that long. But I would say that's something that's still really limiting this field, is batteries, and then in small lightweight motors that allow you to deliver high torques. So the wearable components, the controls, all of that is things that I think we've made a lot of advances in, but the hardware components are still kind of holding the industry back. And then I guess Scott's last question, you got any guesses about the next big step forward? So when I was looking at jobs after I graduated in the wearable robotics industry, it was like, there's medical applications, there's some companies out there like Google X who are trying to do, who are exploring wearable robotics as well. There's some companies that are trying to do it for all day, everyday wear. And I think we're like, and intentionally with VERVE Motion, my current startup, is we're working to try to solve a very clear need. People are lifting 20 to 30,000 pounds a day, and then we're trying to offload that. I think that's where we start. Is it going to be a mainstream thing? I don't know. Probably not until the battery technology catches up with it, so that you could wear this for longer.
Brendan, I'm going to give you a little bit of a breather and read this question for you.
Okay, thanks, Sally.
doing it all. Jeff Bayard wants to know, what are the significant remaining challenges to solve in order for robotic AFOs to be available to the general population impacted by strokes or muscle weakness?
So that is what Reebok is trying to do right now. They're taking the technology they licensed from us at Harvard and trying to bring it to the general population. I think there's definitely some, as I mentioned, the battery challenges already. For at-home rehab, you can probably get away with a quite lightweight battery if you're only doing it for an hour or two. I would say the biggest challenge I foresee is a lot of what we've been doing so far is level ground walking in the lab, and level ground walking outdoors with maybe some small like hurdles that you have to overcome. I think from a software side, a control side, being able to adapt or being able to detect different environments and adapt to them is probably the biggest challenge. in both for AFOs for at home and for the industry as a whole, is really being able to advance the software side so we can detect these different motions and provide the assistance at the right time.
Great questions. Anybody else? Brendan, this has been fantastic.
Thank you all for listening. Yeah.
And thank you everyone for coming. Watch for more information about Frank Talks, and Brendan, keep doing the good work. Thank you.
Thanks, Sally. Thanks, everyone.